Let the distance from m1, m2, and m3 to the ground be equal to y1, y2, and y3, respectively. Let also the distance from the center of the lower pulley to the ground be equal to y. Let's calculate the length of the second rope. This will be equal to length of this part, which is equal to y minus y2, plus the length of this part, which is equal to pi r, where r is the radius of the lower pulley, plus the length of this part, which is y minus y3. We differentiate both sides of the equation twice and get that 2 times y double dot is equal to y2 double dot plus y3 double dot. Note that the length of the rope and the radius of the lower pulley are constant, so their differentiation becomes 0. We now apply Newton's second law to the lower pulley. The net force will be equal to the tension force from the rope above, let's call that T1, minus the tension forces from the ropes below. Both of them are equal, let's call them T. So the net force on the lower pulley becomes T1 minus 2 times T. The pulleys here are ideal pulleys, so their masses are 0. As a result, the net force on the lower pulley becomes 0. So we get that T1 equals to 2 times T. Note that the acceleration of m1 and the lower pulley are equal in magnitude and opposite in direction to each other. So y1 double dot equals to negative y double dot. We now write down Newton's second law for m1, m2, and m3, taking the upward to be positive. Solving these 6 equations and with a little bit of algebra, it is easy to show that the acceleration of m1 is this result.